Being the most highly regarded mind of his time, Newton, without equal, dominated the popular opinion with his own convictions that light must be fundamentally digital. Light, as he proposed, should be thought of as moving clusters of minute corpuscles, tiny particle-like bodies of light that once again floated upon a luminiferous ether. By the beginning of the 18th century, a whole suite of models took the idea of an ether as granted, and Newton was to be of no exception. His own gravitational ether was in many respects modern, as it described a medium through which the forces of light, electricity, magnetism, and gravity could persist. But as scientific as this sounds, the truth was that both the ether and our interpretations of reality on the whole had far from shed their religious foundations. The ether was still considered to be some version of the Aristotelian purity, only now interwoven with other various heavenly influences. As Newton described, the main phlegmatic body of the ether and other various ethereal spirits moved together as a type of universal vortex that was whipped up and set into motion, at first by the immediate hand of the Creator, and ever since by the power of nature. Thus, perhaps, postulated Newton, may all things be originated from ether. But beyond the views of his era, his hypothesis for a particle-like nature of light was firmly rooted in the evidence-based thinking that we today consider scientific. For example, sound, which had long been understood to move through the air in the form of waves, showcased many attributes that light didn't. Whereas sound waves can travel through pipes and around corners, light can't. But even beyond any direct evidence, there was still plenty of reason for the public to assume Newton's authority on the topic. His revolutionary insights had already revealed how white light was actually made up of all the colours on the spectrum, and that not only could white light be split into the 7 hues of the rainbow, but this spectrum could just as easily be recombined back into white light when passing through the crystal prism. A result that inspired the realization that colour must be a property of light rather than of the material objects themselves. It was also at this time that another vital discovery had been uncovered relating to the speed of light. By using Newton's new gravitational constant, Danish astronomer Ole Rømer had been attempting to predict the orbital periods of Jupiter's moon Io. But his concerns arose when these orbital periods seemed to ebb and flow outside of the predictions set by Newton's equations at various times of the year. A fluctuation that risked jeopardizing the validity of Newton's gravitational equations as a universal constant. Rømer's own moment of brilliance, however, came when he realized that the apparent variations in the results had come about as a result of the Earth's own orbit, as well as the finite speed attributed to the light travelling from Jupiter to Earth. And so, by including the influence of the orbits in his calculations, Rømer was able to broadly calculate the time it had taken for the light to travel the great expanse between the two planets, providing an almost entirely accurate speed of light. But as reaffirming as this was for Newton's theory of gravity, it did little to support his corpuscular theory of light, which was a shame, as it was not without its challenges, such as his explanation for why light might bend when passing from air to water. According to his theory, these light bodies should be subject to the same physical laws as any other projectile. And so with this in mind, he began to imagine the moment of the light's impact upon the water's surface, rationalizing that as the particle moved through the air, it would experience no net force that might move it in any particular direction. But when it closed in on the water's surface, this slight imbalance between the density of the air and the density of the water would lead to a slight acceleration, having gravity pull the particle down towards the water's surface. This then giving rise to the refraction that we experience as light's familiar bending. As an explanation, however, it required that light must accelerate into water rather than slow down. The counter to which was put forward by Newton's most notable opponent on the topic, Dutch mathematician Christiaan Huygens, whose theory of light waves suggested that light would slow when encountering water, though experimental evidence would not be possible until 1850, a near half-century later. Thus, it would take the efforts of the lesser-known genius Thomas Young to devise an alternative approach to the problem. Young's interest in light had come about as a result of his medical studies, though it would have initially been an understanding of sound that inspired his 1801 experiment. As sound waves, or any wave for that matter, move about the medium of their environment, they tend to bump into things, with waves inevitably crossing back through one another, an attribute that tends to cause familiar patterns to emerge. The easiest way of envisioning these is by imagining the ripples that occur when a pair of stones strike the surface of a pond at the same time. As each splash ripples outward, waves pass through one another, causing the surface of the water to amplify a patchwork of troughs and crests called an interference pattern. And it was Young's idea to seek these interference patterns within the nature of light. Like Ibn al-Haytham, Young was able to force light through a single point cut from a sheet of paper that covered a window. Then, by placing a card vertically down the centre of the hole, he further split the beam into two very small and very close equal beams of light. His thinking was that if the light did in fact move through space as particles did, then he should expect to see two distinct clumps of light, where each beam of particles came to land, just as sand would beneath the hole of an hourglass. But if light were to instead move through the holes as waves, then the two beams would disperse in equal directions, resulting in the familiar interference pattern. And to his amazement, there it was. A band of alternating light and dark lines that could only come about as the result of two interfering light waves. Irrefutable evidence that light did indeed act like a wave. And thus he had invented the famous, well, actually, at this point it was still the less famous single hole with the small card across the middle experiment. Not very catchy, I know. But essentially this was it, the famous double-slit experiment. And if you're not impressed by this, don't be downhearted, there is still a part 2 yet to come. Though sadly for Young, as popular opinion refused to detach itself from the powerful influence of Newton, the experiment would be, for the most part, dismissed. But as time passed, and technological discoveries began to compound, it was Young's experiment that stood the test of time, so that by the end of the 19th century, with the coming of thermodynamics and electromagnetism, science had entirely adopted Young's discovery. Light was undeniably a wave, but the question which remained was that it was a wave of what? If you enjoyed that and you would like to watch the next part, I'm going to put the links below. Otherwise, the full 1 hour deep dive into the history of light is currently available on our homepage, so feel free to check that out. Otherwise, much love, and I hope you all have a wonderful, wonderful week. See you later.